In the realm of modern technology, the interaction between humans and computers has evolved beyond the keyboard and mouse. One of the most intriguing and complex areas of this evolution is natural language processing, NLP, a field that sits at the intersection of linguistics, artificial intelligence, AI, and computer science. NLP strives to equip machines with the ability to understand, interpret, and generate human language in a way that is both meaningful and contextually relevant. This video delves deep into the world of NLP, exploring its history, core concepts, major techniques, real-world applications, challenges, and future prospects. Before we begin, please consider subscribing to the channel, giving this video a thumbs up and sharing your thoughts in the comment section. The evolution of natural language processing. The origins of NLP can be traced back to the 1950s when the field of AI first emerged. Pioneers like Alan Turing and Warren Weaver began to envision machines capable of understanding and producing natural language. Early attempts, such as the ELIZA program developed by Joseph Weizenbaum in the 1960s, focused on simulating conversation rather than truly understanding language. ELIZA employed simple pattern matching techniques to provide scripted responses, often leading users to believe they were interacting with a human. The true breakthrough in NLP arrived with the advent of deep learning in the 2010s. Deep learning models, particularly recurrent neural networks, RNNs, and later, transformer models, demonstrated remarkable success in language understanding and generation tasks. The introduction of word embeddings like word2vec and glove allowed words to be represented as dense vectors, capturing semantic relationships and context. The transformer architecture, introduced in the seminal paper, Attention is All You Need, by Vaswani et al., 2017, revolutionized NLP. Transformers leverage self-attention mechanisms to process sequences of words, enabling the model to capture long-range dependencies and contextual information effectively. This architecture paved the way for models like BERT, GPT, Generative Pre-trained Transformer, and its subsequent iterations, which have achieved state-of-the-art results across various language tasks. Core concepts in natural language processing. 1. Tokenization. Tokenization is the process of breaking down text into individual units, usually words or subwords, known as tokens. This step is crucial for NLP tasks as it provides a structured representation of raw text that can be fed into models. Tokenization also involves handling punctuation, special characters, and other linguistic nuances. 2. Part-of-speech tagging. Part-of-speech, POS, tagging involves assigning a grammatical category, such as noun, verb, adjective, etc., to each word in a sentence. This process aids in understanding the syntactic structure of sentences and plays a pivotal role in various applications like text summarization, machine translation, and grammar checking. 3. Named entity recognition. Named entity recognition, NER, involves identifying and categorizing named entities, such as names of people, organizations, locations, dates, etc., within a text. NER is crucial for information extraction and knowledge graph construction, enhancing the machine's ability to comprehend the content of the text. 4. Sentiment analysis. Sentiment analysis, also known as opinion mining, gauges the emotional tone or sentiment expressed in a piece of text. It categorizes the text as positive, negative, or neutral, enabling businesses to gain insights from customer feedback, social media posts, and reviews. 5. Machine translation. Machine translation is the process of automatically translating text from one language to another. This application has evolved significantly over the years, transitioning from rule-based approaches to data-driven methods, and eventually benefiting from the capabilities of deep learning models like transformers. 6. Text generation. Text generation involves creating coherent and contextually relevant text based on a given prompt or input. While early methods were often rule-based or template-driven, modern approaches harness the power of generative models like GPT, which can produce human-like text by learning from vast amounts of training data. 7. Question answering. Question answering, QA, systems aim to provide accurate and relevant answers to user queries posed in natural language. These systems typically involve understanding the question, retrieving relevant information from a knowledge base, and generating a concise and informative response. Major techniques in natural language processing. A. Rule-based approaches. Rule-based approaches in NLP involve crafting explicit linguistic rules and patterns to analyze and generate text. While these methods offer interpretability and control, they struggle with the intricacies of language and often require extensive manual effort to adapt to different languages and domains. B. Statistical methods. Statistical methods employ probabilistic models to infer patterns from large amounts of linguistic data. Techniques like n-gram models, hidden Markov models, HMMs, and conditional random fields, CRFs, have been used for tasks such as language modeling, part of speech tagging, and named entity recognition. C. Machine learning. Machine learning algorithms have significantly impacted NLP by enabling models to learn from data. Supervised learning, where models are trained on labeled data, has been employed for tasks like sentiment analysis and text classification. Support vector machines, SVMs, decision trees, and neural networks have played crucial roles in this realm. D. Deep learning and neural networks. The rise of deep learning marked a turning point in NLP. Neural networks, particularly RNNs and CNNs, convolutional neural networks, have been used for tasks like sequence-to-sequence learning, machine translation, and image captioning. The transformative power of neural networks reached its zenith with the introduction of the transformer architecture and its derivatives, which excel in capturing contextual relationships in text. E. Transfer learning and pre-trained models. Transfer learning involves training models on a large dataset and then fine-tuning them for specific tasks. Pre-trained models, such as BERT, GPT-3, and T5, have achieved remarkable results by learning representations of language from massive corpora. This approach reduces the need for extensive task-specific data and accelerates progress in various NLP applications. Real-world applications of natural language processing. Virtual assistants and chatbots. Virtual assistants like Siri, Alexa, and Google Assistant have become an integral part of daily life. Powered by NLP, these systems can understand user queries, provide information, and perform tasks ranging from setting reminders to making restaurant reservations. Chatbots, which simulate human conversation, are used in customer support, e-commerce, and other domains. They leverage NLP techniques to comprehend user input and generate relevant responses, enhancing user experience and streamlining interactions. Text summarization. Text summarization involves condensing lengthy documents or articles into shorter versions while retaining the core information. This application finds utility in news aggregation, content curation, and information retrieval, enabling users to quickly grasp the key points of a text. Language translation. NLP has revolutionized the way languages are translated. Modern machine translation systems, such as Google Translate and DeepL, employ neural machine translation techniques to provide more accurate and fluent translations across a wide range of languages. Sentiment analysis in social media. Businesses leverage sentiment analysis to gauge public opinion on social media platforms. By analyzing tweets, comments, and reviews, companies can understand customer sentiment, identify trends, and adjust their strategies accordingly. The future of natural language processing. Multilingual and cross-lingual understanding. The future of NLP lies in models that can understand and generate multiple languages accurately. Cross-lingual models that can transfer knowledge from one language to another will enable better communication and understanding across cultures. Contextual understanding. Advancing models' ability to understand context will be a key focus. NLP systems need to grasp not only the local context but also the broader context of a conversation or text to generate more meaningful responses. Few-shot and zero-shot learning. Current NLP models often require large amounts of task-specific data for fine-tuning. Future models will likely require fewer examples, enabling effective learning from limited data. Improved ethical considerations. As NLP technology becomes more integrated into society, addressing bias and ethical concerns will be paramount. Researchers and practitioners will need to develop methods for identifying and mitigating biases in models and datasets. Human-machine collaboration. Rather than aiming for fully autonomous AI, the future of NLP may involve more collaboration between humans and machines. AI could assist humans in tasks like content generation, translation, and summarization, enhancing productivity and creativity. Natural language processing has come a long way since its inception, transforming the way humans and machines interact and communicate. From rule-based systems to deep learning models, NLP has achieved remarkable progress in understanding, interpreting, and generating human language. While challenges like ambiguity, bias, and ethical concerns persist, the potential for NLP to revolutionize industries such as healthcare, law, and customer service remains undeniable. As researchers continue to push the boundaries of technology, the future promises even more advanced language models that bridge the gap between human expression and machine comprehension.